Welcome to Engineering with Rosie and to part 2 of my series, How Does a Wind Turbine Work? In the first video we saw how much energy is in the wind and how efficiently wind turbines are able to capture it and convert it to electricity. In this video I'm going to take you through the basic aerodynamic calculations that you will need to understand how a wind turbine transforms the kinetic energy in wind to the mechanical energy of the rotating shaft. The basics of wind turbine aerodynamics are the same as classical aerodynamic theory. Another way of saying that is that a wind turbine blade uses the same aerodynamic theory that allows aeroplanes to fly. Air flows over an airfoil at an angle of attack, alpha, which causes a lift force L in the direction perpendicular to the airflow and a drag force D in the direction opposite to the airflow. Wind turbine blade faces are a slightly more complex situation than an aeroplane wing though, since a wind turbine blade faces airflow not just from the wind but also from the rotational motion. And there's a further complication to the flow direction that the blade sees that occurs because the wind speed in the stream tube is not constant. The inflow needs to be taken into account when you're analysing the aerodynamics using axial and tangential induction factors A and A prime. The flow speed and angle of attack varies along the blade span depending on the sum of these vectors. The wind speed, V infinity, the turbine's rotational speed, omega, and the flow factors, A and A prime. You can use trigonometry to determine the local wind speed and angle at every location along the blade span. And you can see that at the blade root, the local wind speed and direction is similar to the wind speed. Whereas at the blade tip, the rotational speed has a much bigger effect than the wind speed. Once you know the local wind speed and angle of attack, you can use the classical two-dimensional lift and drag equations to find out the forces at each location along the blade. For an aeroplane, the lift force acts against gravity and the drag force resists forward velocity. But for a wind turbine, the lift and drag forces aren't directly relevant to rotor mechanics. You need to resolve them into components that will cause the blade to rotate, called torque, and the force that will try to push the turbine over, called thrust. You need to use trigonometry again to get these components.
For the torque, it's the lift force times sine of psi minus the drag force times cos of psi times the radial location of the blade element. For the thrust force, it's the lift force times cos psi plus the drag force times sine of psi.
If you split the blade into a number of sections and add the torque and thrust for all of these sections, then you will get the total torque and thrust. And then to get the power of the turbine, you multiply the torque by the rotational speed, omega. This method of splitting the blade into sections or elements that are analysed using classical 2D aerodynamic equations is called BEM. And it is a very simple and common method to analyse wind turbine aerodynamics, but it does rely on some assumptions and some limitations. It's not completely accurate because, as we saw when we were looking at the stream tube, the flow is not completely two-dimensional. There's inflow caused by the change in wind speed in the stream tube from upwind to downwind. So using two-dimensional analysis will give a small overestimation of the turbine power. BEM also assumes that each blade is operating in clean air, completely unaffected by the other turbine blades. And this is a pretty good assumption for an optimized rotor design or something close to it. But if you were to add more blades or to make them wider than the optimum, BEM would not be able to capture the loss of performance due to the crowded rotor. If each blade is affected by the wake of the blade ahead of it, BEM can't capture that. So you can't use this theory to determine what is the optimum number of blades for a turbine. You need to use a more complex analysis for that. So BEM has some limitations that you need to be aware of. But when you're using it with this knowledge and within its limitation, it is so much simpler than the alternative of a full three-dimensional analysis. And it's definitely good enough for preliminary design of major blade geometry parameters like the number of blades, twist and chord distribution. So that's the basics of wind turbine aerodynamics, how the blades take the kinetic energy from the wind and turn it into the rotation of a shaft, which can turn a generator and make electricity. In the next video, I will show you how you can use this theory and the blade element method to design the geometry of a wind turbine blade. As always, if there were any topics that you found confusing or I didn't explain well enough, then let me know in the comments and I will do my best to answer them. I also like to get ideas for future videos in this way, so let me know if you have any ideas. And if you found this video interesting and want to see more like this, then please remember to like and subscribe and share with your friends. I'll see you next time.